Welcome, this is Dr. G, and in this video I will be introducing kinematics. I'll first go over what kinematics means and what you need to know both theoretically and practically for problem solving, and then we'll focus primarily on the differences between scalar and vector quantities specifically pertaining to kinematics topics such as speed, distance, velocity, and displacement. You got this. And let's have some fun. Let's go. Kinematics is a branch of physics that deals with describing and calculating all aspects of motion. The next topic you'll learn after kinematics is dynamics, and dynamics focuses on understanding the forces that causes the motion. Now, when you learn dynamics, you will need to remember your kinematics because these two topics are linked, and they're linked through acceleration. What I mean by that is acceleration is a very important variable in both kinematics and dynamics. Which means if you're looking for acceleration and you're doing dynamics, you might need to go to kinematics first to find the acceleration before able to do dynamic questions. What you're expected to know in the chapter of kinematics can be broken down into two general categories. The first one is the more conceptual theoretical knowledge, and that includes understanding the difference between scalar and vector quantities, along with the associated terminologies that you have to know. And then there's two graphs you have to understand, the position versus time graph and the velocity versus time graph, both of which will be covered in a video later on. The other part of kinematics, and the main part of kinematics, is the calculation and the actual application of the concepts you know. And that can be further broken down into two parts. The first one is generally called uniform motion. That just means it deals with calculations for all types of motion without acceleration. We call it uniform motion because the word uniform represents not changing or same. So uniform motion just means the same motion, which means your speed or your velocity is not really changing, hence there is no acceleration. Within uniform motion, you have to understand the main equation of velocity or average velocity, and then there's two minor topics including relative velocity and then a two-dimensional application of relative velocity known as the independence of perpendicular vectors. Once you're introduced to acceleration, then we get into a topic called uniform acceleration, which means now, although your velocity and speed is changing, your acceleration remains constant or uniform. Within uniform acceleration, you will be introduced to the big three kinematics equations, which then deals with either horizontal axis plane or vertical plane, which includes free fall. And then you can do this in two dimension, which includes both the horizontal and vertical axes, which is the projectile motion questions. Let's compare and contrast scalar versus vector quantities. Notice underneath the scalar quantities, it says magnitude only. That means scalar quantities only have size or a numerical value. On the other hand, vector quantities include both a magnitude and direction. Now, the direction portion of vectors can actually be a bit misleading. When you're taught this, you will be taught when you're writing any quantity in vector, for example, displacement, don't forget to leave your answer as, let's say, 200 meters west or negative 200 meters to represent going left or something along those lines. Yes, that is true. You do need to take that into account when you're doing directions for vector quantities. Direction aspect of vectors is not just writing a direction as a part of your numerical answer at the end. You need to keep track of the directions throughout your question calculations so you won't make a mistake for your final answer. As you can see here, I've bolded and used color for the main scalar and vector quantities that you need to know for kinematics only. As you can see, the list goes pretty long for both scalar and vectors, but the ones in gray, you don't need to know them for kinematics. A quick note before we go into the actual scalar and vector terms of distance and displacement. In physics, you will be doing questions either in one dimension or two dimensions. In one dimensions, everything's happening on the same plane, which means there's no horizontal and vertical components of something, which means there's no diagonal. In that case, there is no x and y components of anything you're given, so you don't need trigonometry at all. Scalars are only going to be in one dimensions. Unfortunately, you'll be doing majority of your work as vectors such as displacement or velocity or acceleration, and vectors can be either in one dimension or two dimensions, meaning there's going to be now two different planes, which means you'll have x and y components, which means you will need some basic trigonometry to solve these questions. Okay, so now let's talk about the difference between distance and displacement, one of which is a scalar and the other one is a vector. Starting with a scenario here, we're at point A. Let's say you walk up 200 meters north to point B, and then you decide to walk back 200 meters to point A. For the distance, it's quite simple. Just pretend that you're wearing a tracking watch or something that tracks the steps or the distance you've covered. So, does it matter if you're walking up, left, right, or down? No. Distance is distance. So you walk 200 meters up, and then you walk 200 meters down. 200 plus 200 is 400 meters of total distance you covered. Displacement, on the other hand, is dependent on your direction. So it doesn't really care about how many total distance you've covered. It really cares about the net change in your overall position, which we can then write as your final position subtracting by your initial position, or position final minus position initial. In this case, you can see that we really haven't moved. We walked up 200 meters, but we came back down to our original starting point, so we have a net displacement of 0 meters. Now, the equation PF minus PI, that is what defines displacement, but it's not very useful if you don't really know your position. For example, here, we don't even really know what position A is, so we can answer this question conceptually, understanding what displacement means. Next scenario, let's say we start with point A, and this time we walk up 400 meters to point B, and then we turn right and walk 300 meters to point C. Again, distance really cares less about which direction you're going, so we add up our total distance, which is 300 plus 400, which gives us 700 meters. However, displacement is a change in position, right? So we started at point A, and we ended, or our final position is at point C. So our displacement, won't you agree, is actually defined by this arrow. And in this case, you can calculate the actual displacement using Pythagorean theorem here because of the right triangle, and we'll get an answer of 500 meters. Third scenario here, let's say we start at point A. This time we walk to the left 300 meters, and then we come back and walk to the right 200 meters. What will be our distance and displacement? For distance, again, we don't care about the direction at all, so we're going to add up the total distance we covered, which will give us 500 meters. But when it comes to displacement here, our net position change went from A to C, which is moving to the left. And because displacement cares about directions, going to the left is actually going to be negative. So when we walked from point A to point B, our displacement wasn't just 300 meters, it was negative 300 meters. And then when we went from point B back to point C to the right, that is 200 meters. So in this case, we can actually add up negative 300 meters plus 200 meters, which gives us a displacement of negative 100 meters. We can also say 100 meters to the left. We can also say 100 meters west. Either of those three will be okay. Now, just don't do negative 100 meters west or negative 100 meters left. It's almost like a double negative, so please don't do that. Either stick with the negative sign in your answer to represent going left, or don't use negative and actually write the directional word. Just now I mentioned that when it comes to vectors and directions, there's actual mathematical signs associated with directions. So as you can see here, when you go up or to the right, it is positive, and when we're moving down or to the left, it is negative. Pretty standard if you've done math. One thing to note here though is, this is just something for you to use if you have a choice. If the question says that someone runs to the left, and in the question they made left positive, then that's okay. You can keep left positive, and that means the right becomes negative. So it actually does depend on the situation. It's not concrete, but if you do have a choice, I would recommend sticking with this because this is more universal. Now that we know how to associate positive and negative signs to your directions, we can go back to the first example where we walked up 200 meters and came back down 200 meters, and we can solve for the displacement a different way. We can say that for the displacement, when we walked up from point A to point B, it was positive 200 meters, and then when we came back down, it was negative 200 meters, and if we're to add them up, we will get 0 meters, which was the same as our original answer. So although the equation for displacement is technically your final position minus initial position, it's actually not that useful except on graphs and in certain questions where they specifically give you the position of the person or whatever you're talking about. In most cases, it's the best to calculate displacement by just doing what you're doing for distance, which is adding up all the distance you're covering, with the exception that for displacement, you have to include the signs to represent the directions you're traveling and not just blindly add up all the numbers for their values. Now that we know the difference between distance, which is a scalar quantity, and displacement, which is a vector quantity, we can take a step forward and compare speed and velocity. Speed is the distance it took over the time it took. In other words, S equals d over t. Velocity, on the other hand, is the displacement over the time it took, and v is equal to d over t. Notice the arrows above the v and the d. That represents that they are both in the same plane, which means that they're both vectors. So d with an arrow on top is displacement, and d without the arrow on top is distance. Now, to be honest, once you're done the first part of kinematics, which really picky on the scalar versus the vector quantities like distance and displacement, after that, you're dealing solely with displacement, so most teachers won't even really care if you put the arrows above the v or the d and not. Which means if you see a question where there's no arrows above the v and the d, but you're well into kinematics, you can assume they're talking about displacement and velocity. These arrows also serve another purpose, and this one's actually really important. When you're doing questions in 2 dimensions in kinematics, these arrows help remind you that if you're to use these numbers in this equation, the velocity you're using and the displacement you're using has to be in the same plane. Either they both have to be horizontal in the x-plane or vertical in the y-plane. You can't just pluck numbers out of convenience for a velocity and a displacement and crunch it in to get a time, because that doesn't work. You have to use numbers or variables that are within the same plane. So these arrows above the v and the d reminds you that if you want to use a velocity or a displacement in this equation, they both have to be either in the horizontal plane or both have to be in the vertical plane. Now that we know what speed and velocity is, let's see if we can figure that out in the previous 3 examples. Starting with the first example here, let's say this entire trip of going up to B and coming back down took 50 seconds. How would you calculate the speed? Well, we know that speed is equal to d over t, or the distance over time. We know the distance is 400 meters, the time is 50 seconds, so we crunch that in and we get 8 meters per second as our speed. For our velocity, we know velocity is equal to the displacement over time, but since our displacement is 0 meters, 0 over 50 is still going to be 0, so our velocity here is actually 0 meters per second. In the second scenario, let's say it also took 50 seconds and our distance is 700 meters, which means our speed will be 700 over 50, which is 14 meters per second, no directions involved. However, for the displacement, we went diagonally up to the right by 500 meters through Pythagorean. But that's just the magnitude. The direction of the displacement is actually northeast because it's pointing to the top right-hand corner. Now, when we're doing the velocity, we're going to take into account that the magnitude of the velocity will be the magnitude of the displacement over time, which would be 10 meters per second, and the direction will also be pointing towards the northeast, so we put NE. Now, when you're actually doing this question in vectors, your teacher is probably going to want more specific of an answer, meaning what degree or what angle are you going? Are you going north of east by how many degrees or east of north? That will all be covered in my vectors video. And in our final and third example here, let's pretend it also took 50 seconds. If our distance was 500 meters, then the speed would be 500 over 50 or 10 meters per second. And our displacement, we said was negative 100 meters or 100 meters to the left or 100 meters right, which means if we crunch it into our velocity equation, it will be either negative 2 meters per second or 2 meters per second to the left or 2 meters per second to the west. And that wraps up this introduction video to kinematics. Hopefully after this video, you have a good idea of what this chapter is generally about and have a good understanding of the fundamental concepts that you will need to help you as you move deeper into kinematics. If you liked the video, remember to give the video a like, and if you really like the video, feel free to subscribe. It won't hurt. Remember to write any questions, comments, or topic requests in the comment section down below.